This is a topic we can spend a lot of time on, but we're not gonna. I'm just gonna say that when you build optical fiber links, you've got to be aware of a couple things. But the main thing is you got to understand. Okay, here's my launch device. Here's my transmitter on the launch side, and it puts out a signal at this power level. When I get to the other end of that link and I plug into the receiver on the other end, it's going to have a sensitivity that says the signal that arrives here has to be at this power level. All of the stuff in between, whether it's fiber cable, which will have its own, it'll have its bandwidth and loss characteristics just for the cable, and then there's guidelines by which the mated connections have to meet in terms of loss, and then splices as well. So when you figure the loss budget up, you say, okay, if I add up all these points of loss and take that away from the transmit signal, is it going to be enough for the receive side? Right. So there is some math calculation that should be done. Now, a lot of today's testers will go out and and test it and validate it for you, but it's just good practice to make sure you understand. Okay, I'm going from A to B. Here's what I'm sending in power. Here's what I want to receive in power. Does it look like if I build this way, it's going to work? Right? Because you can build it and have it not work, and then you're in trouble. But this test device is what's called an optical loss test set, OLTS, where it's just a light source that launches light into the system, and then a meter that reads at the other end how much was lost over the distance. Right? Very important test set as well. Okay, so we talked about the fact that there's two different kinds of multimode, 50 micron and 62.5. Are they compatible with each other? So let's say, for example, I've got a fiber plant where I've got some older 62.5 and I want to add the newer 50 micron. Can I intermix them?
Depends if your loss budget is.
To a certain extent, yes, you're right.
Because I've seen it in our building where people thought that the orange fiber was 62.5, and in fact they're making orange fiber in
50 micron. Yep. And we've got a slide that talks about color codes, by the way. The answer is the answer that we like to give is no. You need to try to not mix them together if you can help it. Okay. But factually, the answer is it depends. Okay. What would it depend on?
Distance?
No, it would actually depend on which way the light's traveling. Okay. Because what we have here is we've got the cone of acceptance. That's the axis by which light can actually enter the core and stay within it. Right? We won't get into the gory math here, but just understand that beyond a certain angle, light won't stay in the core. Okay? And then it's cast out into the cladding. When I line up a 62.5 and a 50 micron, I can see that the numerical aperture is totally different between the two. So I'm going to lose modes of light depending on which way the light's traveling, right? So if I take a 62.5 and made it to a 50 micron and shoot light through it that direction, what's going to happen?
You'll lose a lot of the signal rate.
You're going to strip off the higher order modes, and you're going to lose a good portion of the light pulse, right? So that's what happens in that direction. Now, is it the same if I go the other direction? If I dump from a 50 micron into a 62.5, what happens? Do I have loss?
You should, because your signal gets stretched out.
I'll have a little bit of loss associated with just the mated connection, but I'm talking about numerical aperture loss. Will there be loss associated with the numerical aperture mismatch?
Potentially gain.
Gainer is interesting. If you looked at it with an OTDR, it might show as a gainer. Okay. What happens is you don't lose anything. Okay. The light fills the core of the 62.5, and eventually, as it continues to travel down, it's going to occupy those higher order modes. The light pulse will spread. Okay. But because of that, it is going to reduce the overall bandwidth of the link because you are spreading the pulse. Okay. So what the problem with that is that it depends on which way you're shooting the light.
So basically, if you're on the site and you've got two flavors of stuff, you want to put and the client screwed up and bought this, not the right stuff that you really needed, but he has both stuff there. So put the smaller stuff first in the line and then go to the bigger stuff.
You'll drive yourself crazy trying to figure that out in the field. So what my suggestion is this: if you're in a situation like that, put it together, see if it works. And if it works, hey, I would advise the customer at that point, you're mixing 62.5 and 50 micron, and it's not the best idea.
Are there multimodal converters to ease that transition? Exactly. Do you offer some adapters?
So there are manufacturers who will make a cable assembly that goes from 62.5 to 50 micron, but our recommendation is always it's best to make that change in an active device. So in other words, if I've got a switch
Modular.
where I've got 62.5 and I have the ability to add a module that will actually operate at 50 micron instead, I'll make the conversion to the switch. That way I know the plants are separate and I'm not relying on a cable assembly to make that happen. That's usually our recommendation. Okay, other sources of loss. We talked about numerical aperture mismatch. That was the 62.5 and 50 micron. You can also have lateral misalignment of the end faces. Notice also here, we haven't talked about it yet, but we're gonna. When I have optical fiber connectors come together, they physically touch. Right? The end face glass physically touches the other piece of glass. Right? And we'll understand more about that in a second. But so if I have lateral misalignment, I'm going to have loss associated with that. Angular, obviously, an air gap is a big source of loss if it happens. What can cause that? Anybody?
You don't have the connector snapping.
Or yeah, that, or there's another thing which we'll get to. Core diameter mismatch. This doesn't happen often unless you're really, I mean, obviously numerical aperture and core diameter are kind of the same thing, but this image almost makes it look like they're mating single mode with 62.5, and that would never happen. These forms of loss are really minimal. But there's one that's really big that's not on here. What is it? What's the biggest source of loss in optical fiber links? Number one.
Dirt.
Dirt. Who said that? Winner. Water bottle or stadium blanket?
Oh, I'm cold.
Okay. Dirt. Number one preventable cause of loss in fiber optic circuits.